Şimdi videoyu da açayım da onun açısını nasıl ayarlayacağız? Videomuza göre.
Çok göğüs böyle karabayı sıkıyormuş.
Şöyle mi? Gene böyle olacak herhalde hocam. Yani ben aslında şeyde görünsün istemiştim ama neyse.
Zaten çatıya göstereyim mi?
Ekranı biraz yazayım. Şurada da bir şey.
Yok, zaten canlı yayını gözüküyor. Bunu açtığınız zaman sunum gözükecek hakkında.
Tamam, okey. Okay, welcome everybody. Our first presentation is from Emine Yalman, and their title is the utilization of biomass hard carbon in energy storage. And
Bari şurayı kapatayım, ben kendimi görmüyorum, tutumunu göremiyorum.
sonra da bunun çalışması lazım. Şöyle hocam, şurada dursa siz rahatsız eder mi? İsterseniz şöyle yapayım.
Şuna tıklasanız kayboldu. Sadece görünüyoruz. Good afternoon, everyone. My name is Emine Yalman. I am a PhD student and a research assistant in Iskenderun Technical University. My presentation title is Utilization of Biomass-based hard carbon in energy storage. So, why biomass-based carbon instead of fossil fuel? Because biomass is seen as an alternative precursor for carbon production due to its wide availability, abundance, sustainability, clean, renewable, and low-cost productions. So what is hard carbon? Hard carbon, which is also called as non-gravitizable carbon, is very attractive due to its high capacity and fast rate capability. Hard carbon is a solid form of carbon that cannot be converted to graphite by heat treatment, even at temperatures as high as 3000 centigrade degree. Currently, we are working on some pomegranate waste. So why pomegranate waste for hard carbon? Because Turkey is the natural spreading area of pomegranate, and pomegranate cultivation is carried out mostly in Mediterranean, Aegean, and Southeastern Anatolia regions. The change in pomegranate production in Turkey on a yearly basis can be seen in the figure. So accordingly, while the total pomegranate production in Turkey was 59,000 tons in 2000, this amount increased every year and reached 537,000 tons as of 2018. And according to 2019 data, pomegranate production is carried out on a total of 300,000 hectares. Problem statement. Along with the production of pomegranate, there is an increase in pomegranate wastes. In this context, it is believed that pomegranate waste tend to create an environmental problem. As it is well known, fossil resource reserves are limited and cause significant environmental pollution. Therefore, there is an urgent need for a clean and sustainable raw material as alternative to fossil source in carbon production. In this study, application of state of biomass-derived hard carbon materials and hard carbon potential of pomegranate membrane in energy storage system will be presented. As methodology, a literature review was conducted using databases such as Web of Science and Scopus. Numerous studies over the last decade on the use of biomass-based hard carbon in energy storage systems have been collected and then summarized and analyzed. It is aimed to increase research studies on the subject by analyzing and researching current studies. Finally, characterization of pomegranate membrane was performed. Here we can see application of biomass-based hard carbon in lithium-ion battery. And here we can see application of biomass-based hard carbon in sodium-ion battery. Here we can see application of biomass-based hard carbon in potassium-ion battery. And finally, here we can see application of biomass-based hard carbon in supercapacitor. From these results, it is clear that although hard carbon obtained from various biomass sources has started to be used in energy storage, there is still an urgent need to improve many parameters, such as capacity and cycle performance of the systems into this technology. Here we can see XRD pomegranate membranes. Result shows 002 and 101 diffraction of graphite and structure of membranes close to the typical XRD pattern of disordered carbon. Here we can see FTIR of pomegranate membrane. Result shows that pomegranate membrane consists of aliphatic compounds. Here we can see SEM image of pomegranate membrane. Image shows that pomegranate membrane has a hollow structure, and it is expected that this structure will facilitate ion transfer. Consequently, considering many parameters, cost, supply, and efficiency, it has been lasting results when used as an electrode material and is an open field for improvement. And pomegranate membrane is a potential material from which hard carbon can be obtained in the application of energy storage systems. My references. Thank you for your attention.
Thank you, dear Emine Yalman. Is there any question? Okay, we thank Emine, and we need to solve the problem with the Zoom. We have some participants waiting our waiting room. And we need to accept them. Önce bir şunu halledelim. Şunu yeniden gönderdim mi? Bildirim nereden gelecek?
Tekrar
Hocam YouTube arkada açık kalması gerekiyor. Açık mı acaba? Açık burada. Tamam. Şu işi bir şey yapabilir miyiz? Çünkü gelenleri alamıyoruz. Yani onlardan onaylayacağız. Bildirimleri veriyorlar. Bir sonraki konu online. Onu
bizden bir telefondan gelirse kabul edebilir aslında.
Ee, Okay, our next speaker is Sezen Özçelik, and her presentation title is Copper Ferrite Nanoparticles, Structural Magnetic Optical Photocatalytic Activity and Bloodcomb. Can you hear me, dear Sezen?
Yeah, I hear you.
Will you
Ca-
share your presentation?
Just a minute. I'm trying. Paylaşım engellendi diyor arkadaşlar. Nasıl yapacağız onu? Ekran paylaşımı diyorum ama.
I will solve. O zaman onu host yaparım. Can you try again?
No.
Okay. Later give me the host again, okay? I will make you host, and now you can share your screen.
Yes. Okay.
Yeah. Ahora se pone un 70% de...
Başlayayım mı? Bekleyeyim mi?
Vale, ahora como no, no, que...
You can start.
Okay. Thank you.
Te he dicho que pares a 9 y ya seguiré un directo. A 9 se Bueno, entonces cuando te
Hello, dear colleagues. My name is Dr. Sezen Özçelik. I'm working in Hakkari University. Today I will talk about copper ferrite nanoparticles, structural, magnetic, optical, photocatalytic activity, and blood compatibility properties. The synthesis and investigation of magnetic nanoparticles have been playing an important role in several applications areas, such as semiconductors, sensors, nano-device, MR imaging, high-density magnetic storage, biomedical and pigment applications, and control drug delivery applications. Among the magnetic nano-size materials, in addition to iron oxide, other iron-containing materials also possess the magnetic properties required for biomedical applications. Ferrites are materials that are extremely valuable and suitable for other application areas such as MRI and magnetic hyperthermia. Among the magnetic nanoparticles, spinel ferrites are shown by the chemical formula of M ferrites, where M refers to a divalent cation such as cobalt, copper, iron, manganese, or nickel. Among spinel ferrites, especially cobalt ferrite and copper ferrites, is the focus of attention in physical, chemical, and medical aspects due to their high coercivity, significant mechanical and chemical stability, and high magnetocrystalline anisotropy. Up to now, copper ferrite spinel is widely used in different fields, including heterogeneous catalysis, photocatalysis, photocatalytic hydrogen evolution activity, energy storage, anode material for batteries, high density magnetic storage for high performance spintronic devices. Additionally, its usage is further extended to photocatalytic degradation of methylene blue, photocatalytic efficiency in the decolorization of methylene blue, biomedicine and drug delivery, magnetic resonance imaging, magnetic separation of cancer cells, and antibacterial activities. Although copper is an essential micronutrient, also the cofactor of several enzymes involved in human metabolism, it shows toxic effects at elevated concentrations. This study also identifies the potential effectiveness of copper-ferrite nanoparticles in degradation reactions of organic molecules by photodegradation. For this purpose, photocatalytic activity of copper-ferrite nanoparticles towards crystal violet was studied.
Déjame anotar los cuadrados. Vale, pues cuando me digas,
Luis,
¿estás
I
preparado?
hear you. Thank you.
Ya.
Experimental procedures. The co-precipitation method was used to prepare copper-ferrite spinels ferrites to fabricate nanocrystalline copper spinel ferrites, iron nitrate nanohydrate, and copper 2-nitrate hexahydrate, which are of analytical graded alpha ether, were preferred. In the experimental procedure, the weights of chemicals were stated in accordance of the stoichiometry between ferrite and nitrates. Thank you, Luis. First, the mixture of 0.2 molar iron 3-nitrate nanohydrate and 0.1 molar of copper 2-nitrate hexahydrate was dissolved in the ionizing water of 100 milliliter. Then approximately 30 microliter of oleic acid was dropped into the solution as an active agent. For homogeneous and uniform temperature distribution, the solutions were mixed in an ultrasonic homogenizer at a fixed temperature of 80 centigrade degrees in the water for 2 hours in a continuous mode. Then, in order to reach to 9 of pH value, the sodium hydroxide solution was added by slow degrees in 1 hour time. Finally, the remaining precipitates were centrifuged in distilled water. In order to obtain nanospinel ferrites, copper ferrites, all precipitates were desiccated at 18 centigrade degrees under vacuum for 8 hours and calcinated at a temperature value of 500 centigrade degrees under air condition for 2 hours respectively. And then results and discussions. The first one, XRD results. All peaks illustrate almost the single phase of copper ferrite spinel. The nanoparticles have a cubic structure with a space group FG3M and 5 secondary phases having very low intensities were observed. The second one, SCM results. SCM results was used to study the morphology of copper ferrite nanoparticles as shown in figure A, B, C, D. As can be seen from figure, the copper ferrite nanoparticles do not have a full shape due to the agglomeration. And the third one, photocatalytic properties. Photodegradation of crystal violet, CV, as we see, under 254 nanometer irradiation was carried out to evaluate the photocatalytic properties of copper ferrite nanoparticles. Oxidative stress leads to numerous pathologies such as altered endothelial cell function, leading to vascular disorders, oxidative denaturation, hypertension, and also hemolysis. Reactive oxygen species are one of the most important responsibility of these pathologies, which can also be used to degrade organic pollution agents like hydrocarbons, dyes, or pharmaceutical in contaminated water. And then in this study, crystal violet, which is a common organic molecule in textile wastewater, was used was used as a model organic molecule to diagnose the photocatalytic properties of copper ferrite nanoparticles. And crystal violet was also chosen due to its availability, low cost, high color intensity, even at low concentration. And then variations in the UV visible spectrum of nanophotodegraded CV in aqueous suspension of copper ferrite nanoparticles with the variation of time were shown in figure you see. As can be seen from figure, that the absorption band intensity was gradually reduced with increase of time from 0 to 420 minutes. The intensity of the characteristic band at 591 nanometer weakened after 420 minutes under the effect of 254 nanometer irradiation, indicating the degradation of CV by copper ferrite nanoparticles. The degradation percentage of CV was calculated using equation given below. You see in slide, where C0 and CTR is initial and at time T, CV concentrations respectively. Photocatalytic properties of copper ferrite nanoparticles were investigated using 3 different kinetic models, namely 0 order, 1st order, 2nd order. The equations describing each kinetic model are given in equations in slide you see. Where K first and K second corresponded to photocatalytic degradation rate constants. All variables used in the calculation of kinetic parameters were determined using the calibration equation obtained from the CV calibration curve as seen in figures. Calculated rate constants from each kinetic model as well as the correlation coefficient of each kinetic equation were listed in table 0 order, 1st order, 2nd order you see in slide. The percentage of CV removed by copper ferrite nanoparticles reaches 55.4% after 1,440 minutes. Photocatalytic activity of copper ferrite nanoparticle can be attributed to the possible structural defects of trap states and the strong orientation ability of copper ions in the octahedral structure. And then results represented the capability of copper ferrite nanoparticles to degrade CV under 254 nanometer irradiation. And the last one, blood compatibility test. The main reason for the biological incompatibility between red blood cells and iron-containing nanoparticles is due to the high activity of iron in chemical and biological processes. These unwanted interactions can be avoided by using ferrites for better hemocompatibility. In a related literature study, magnetic copper ferrites nanocrystals were used in the separation of histidine-rich proteins such as hemoglobin. Researchers focused on the selective binding capacity of hemoglobin by copper ferrite nanocrystals and reported 4,475 milligram hemoglobin absorption for each 1 gram of copper ferrite. Hemolytic activity tests are the most applicable and scientifically accepted method that enables the determination of the biocompatibility properties of a newly synthesized material. In this study, we analyzed the hemolytical potential of copper ferrites using healthy human erythrocytes. And figure exhibits the UV spectra of erythrocytes suspension treated with the PBC alone. Copper ferrite nanoparticles with 2 different concentration, 1 milligram milliliter and 5 milligram milliliter. In blood samples treated with copper-containing ferrites, absorption peaks at 540 nanometer and 580 nanometer corresponding to oxyhemoglobin completely disappeared marked with arrows in figure. In conclusion, I say the co-precipitation method using ferrit iron 3 nitrat nanohydrat copper copper 2 nitrat hexahydrat was used to synthesize copper ferrit spinel ferrits. Produced nanoparticles were chemically pure in terms of secondary phases and exhibit an agglomerated structure. The copper ferrit nanoparticles have a cubic structure with a lattice parameter 8.45 angstrom and the space group FD3M. The direct and indirect gap energies of the copper ferrit nanoparticle samples were deduced as 3.24 and 3.60 UV respectively from UV visible diffuse reflectance measurements. Photocatalytic activity measurements show that while copper ferrit nanoparticles could degrade 55.4% of total CV after 1,440 minutes. Among three kinetic models, second order model showing the highest correlation coefficient was found as the most suitable model to explain the experimental photodegradation data. Higher photocatalytic activity of copper ferrit nanoparticles was attributed to the possible structural defects such as trap status and the strong orientation ability of copper ions in the octahedral structure. Thank you for your attention.
Thank you, dear Sezen Özçelik. Is there any question?
Thank you.
Thank you for your presentation. And now could you make us again host?
Okay. Okay. I can hear you. Just a
No.
moment.
Okay.
No. Post yapacaksın bize.
Ah, Can.
Ne haber?
Ben şu an bilgisayarı kullanamıyorum, özürlü gibi. Aman Tanrım.
Konferanstasın, farkındasın değil mi? Baş başa konuşmuyoruz.
You need to come our GAZI hall and make us host again. Then we can share the presentation from Can Özçelik.
Okay.
Niye kemer almadan ki direkt onu açtı?
Nasıl?
Masa üstüne alsaydı onu da açsaydı. Onu da açacağım. Ondan yavaş açıldı.
O kadar kaliteli miydi? Bilmiyorum.
Çok yüksek dosya çünkü. Boyutu.
We have a technical problem here.
Ama şuna bir şey yapalım ya. Admit yapalım ya. Reis geldi. Bir şey söyleyeyim, çıkar. Evet, çok mantıklı. Yanlış bilgisayar. Bir saniye, dur, bir şey demeyeceğim. şey yapabiliriz. Share screen. Hangisi? O desktop mu? Doğru mu yaptık? Emin miyiz?
Sen neyse seni sunamam. Şu arkadaşsın.
Bu çalışmıyor mu?
Çalışmıyor.
Bak mouse orada, burada değil.
Buraya geldi.
Tamam, dur. Evet.
Okay, now our next speaker is the Can Özçelik, and his presentation title is Fabrication of Large Scale Bismuth-based Superconducting Plates via Laser Method.
Yes. Hello, everyone. Today I'm going to talk about the fabrication of large-scale bismuth 2212 superconducting plates with laser method. First of all, I am Can Özçelik. I am a PhD student and research assistant in University of Zaragoza. First of all, our main objective is use it to electrical applications in the future and the shape materials in different geometries as we want. Generate texturing protocols that can be scaled to process big size sample and machine ceramic samples without crack generation. It developed to laser technologies. To make a big sample, we need to make a texturing, align the grains to parallel to the surface and to improve to superconducting. Here is it that we have used the laser zone melting technique. First of all, bismuth 2212 grains growth perpendicular to the solidification front. Important to obtain a stable molten volume, to obtain a solidification front that allow to orient the superconducting grains in the correct directions. And we applied the laser to our materials as shown in the figure. You can see the line for the molten materials, and we need to move through the surface. Here is it, the material we put into the laser system moves in the direction of arrow at the certain speed. Laser application is made in the form of line. You can see that our video, and you can see that our surface molten area, molten zone. And here is that laser line scanning is that our aim is to heat the material without breaking it. The laser speed must maintain in order to molten volume. If it is slow, molten volume should be cooled down. For example, the movement speed should also be suitable for this because the orientation of the grains will be better. Because of it, we use that to these parameters. NIR radiation, pulse duration higher than 10 nanoseconds, and laser scanning speed higher than 2,500 millimeter per second, and sample speed lower than to 100 millimeter per hour. But this is the important things. We made these treatments at room temperature. After that, we made it to surface. We are looking to surface texture. This one is the cross sections, SEM pictures. Here is it. We can see that the solidification front is very planar in the full width of the sample. This will improve the orientation of grains that grow perpendicular to the solidification front. We can see that the left pictures, and we can see that our grains is well textured and the well-oriented region. And during the incongruent solidification process, we saw the two different phases. These are bismuth-free and the bismuth-rich phases. These facilities, the detection of the grain texture. And here is that one of the parameter study is influence of the sample speed. Microstructure is controlled with the laser parameters, decreasing the sample speed, the length of the superconducting grains increases and their orientation improves. In the sample with 425 millimeter per hour has two big regions with very good texture and orientation. And here is it that this is important to control the orientation of grains in the cross sections of the samples. For instance, if we checked to 25 millimeter per hour, we can see that the thickness of the region with good texture is 50 micrometer. We can see that the left picture. And right side is that in the cross sections also we need the planar solidification front that aligns grain, and grains are near parallel to the sample surface, and grains change to be perpendicular to the sample surface. This treatment we made at the room temperature, but we have a big problem at the room temperature. This one is at the crack generation. Unwanted cracks occurred in the sample we prepared at the room temperature. Yes, it's better. Cracks are produced the thermal stress associated with the temperature gradients induced during after the laser process. It is not possible to produce the sample higher than 1 centimeter at the room temperature without cracks. Because of it, we measured the area around 0.85 around here between two cracks. And after that, we measured 0.55 centimeter. We found the critical current 6 amps and critical current per width is 7.1 amp per centimeter. What we are doing, we need to solve this problem. How can we solve it? We use that the laser furnace system is to reduce the temperature radiance, avoid the crack generation. Sample is higher temperature in the furnace. When we apply to laser treatments, sample temperature is at 375 Celsius. We use these parameters: sample temperature, scanning speed, sample rates, and we use these ones because we don't want to different heat on our surface, our samples. We want to our samples everywhere must be same heat, same temperature. Here is it. We can see that left pictures, these ones, we understood. Unwanted cracks is prevented as seen this picture. Molten region depth here is that increased. It was 10 times more or 11 times more. This one's because it was 50 micrometer. This one is 587. And this is our main topic is that the first solve this crack problem. Second main is difference to increase the thickness of the solidification front, which will allow to current to our surface, our flow. The reason we want to keep it white is to allow more current to flow the surface. Finally, grain orientation is very well on the center of the sample. Here is it. And deviate at the corner. We have some problems here. The circular sample is our circular sample. We have the problem this corner and this corner. This one is the deviate. And we don't want to deviate. We cut the sample. We cut it because there has been a deviation in the corners, and for this reason we choose next treatment future studies. We choose a rectangular material, and we cut like that, around 2.5 centimeter. And we have characterized center of the sample with 2.5 centimeter. In the sample of room temperature is maximum width was less than 1 centimeter. And we found the critical current is 204.24 amps. And critical current per width is at the 81.7 amps per centimeter. And here is that after that circle sample, we used that 8 by 8 samples. It was the rectangular sample. We expect that the critical currents higher than 650 amps. But we have the problem. This the maximum current in our current supply is 525 amps. We need to cut the sample for electrical characterization. And we cut this sample like this. And after that, we made the measurement. After the cutting, we saw the critical current was in line with our expectation. This one is 340. And final first conclusions. Laser melting thickness allow to induce the texture in sample. This has been checked when the width is close to 80 by 80 millimeter square, can be scaled to higher dimensions. And second one is when we increase the size of the sample, the ratio of critical current per width is maintained. The performance of big size samples is similar to that of the small samples. And we used to laser machining because we had a problem for cutting our samples. This ones, we use that laser machining prevent cracks during the cutting process, control the heat accumulation, and to prevent these cracks. We use that this one's ultra short laser pulses to reduce heat accumulation. We use that the grain radiation pulse duration 249 femtosecond. And we try to many different conditions in the grain laser. We changed the frequency and speed to keep the rate constant. And by looking at these results, we can see that the different depth of our samples, and this one is around 1.5 micrometer between these samples. And here is that we see that same frequency, and here is that the different speeds. If we compare it, this one's here is the molten region, melting area is 396 micrometer. This one, if we look here, this one is 8 micrometers. We want our sample is that we need to control the melting. As we can see here, and there is a lot of melting in the this picture. This one is the uncontrollable level. But right side, we can control to 8 micrometer on our samples. After that, here is that we can see that we change everything, and we can see the different surface or samples. There is a flatter surface at the high frequency. We see that the frequency and speed decrease. We can see that rougher and heels. Some years we can see that here. This material is has two different phases, and they have two different melting points, and one phase melts easier than other phase. Because of it, we can see that the low frequency and the low speed, this one is hills and roughers. Here is that after the applying the laser to the surface, we examined in SEM. We tried the many different conditions and found that the most efficient was 200 kilohertz, 300 millimeters per second speed. We can see that here depth is 103 micrometers, and there is we have very little melting on our surface, but we can control this melting. The texture of grains reach the surface of the machined region, and this one, after the treatments, this one is our best ones. Yes. And second conclusion is that we can control to machining without crack generation and maintaining molten volume. Thank you. Gracias. Teşekkürler. Who, anyone has the question? Yes, of course.
Start with the furnace, laser furnace.
Here, yes.
I think there is a zone and the width between the laser and as you know that to eliminate cracks, you need the qualification
Yes.
and you need a mass, you need a heat.
Yes.
To eliminate the cracks.
Mhm.
But I suggest you, or I don't know, have you tried one more zone? For instance, in the crystal growth, we generally use 2, 3, or 7 zone furnaces.
Yes.
To eliminate the cracks. Why?
Mhm.
You heat your material. Then, if you suddenly cool this material,
Yes.
there are so cracks.
Yes.
But
This one is a cool down.
yes, the cooling down process is also gets so time as the heating process.
Yes.
So to eliminate the cracks, you may try one more zones.
Mhm.
So you can make a colder gradually.
Yes.
So you can eliminate the cracks.
Yes, maybe, probably, but first one we use that first laser. This method we had the problems of our surface. We use that the laser method our surface, but this heating and upper and bottom heating is so different.
Yes.
Because of it, our samples cracks or not bottom or upper. Everywhere is a different temperature heats. Yes. How can we think about how can we do it? We have to make same temperature, same heat everywhere is our sample. We try it. This one is we solve the problem.
Yes.
And this one's better one, yes. Because if you're going to lower, we have to cracks is continue.
You didn't get the material suddenly. You wait.
Yes. We put to here, we just waiting to a little bit.
Yes.
Inside, when it comes to here, we after that suddenly using the laser, after that going to slowly again. Not suddenly go back. No, is we going to slowly because of it. Here is that this one is the scanning speed. This one is the sample speed is lower than this one. Going to slow. Yes. Thank you very much. Okay, thanks.
Thank you, Can Özçelik. This is the last presentation before our coffee break, and we will meet again 3:30.